Most chemical reactions are permanent. You mix reactants, form a product, and it stops. But certain chemical systems don't stop. They can seamlessly run backward. We denote these systems using the reversible reaction symbol, two half arrows pointing in opposite directions, rather than the standard one-way arrow. A clear example of this is the chemical diagnostic test for water, which relies on a compound called anhydrous cobalt-2 chloride. Without water, anhydrous cobalt-2 chloride is blue. Adding water makes the structures bond with water molecules, rearranging into a vivid pink hydrated structure. Heating strips the water away, returning it to blue. The equation is CoCl2 plus 6H2O, reversibly forming CoCl2.6H2O. Because the products in the system can continuously reform the original reactants, we can manipulate this chemical loop. By altering the environment, we can control exactly what the reaction outputs. To maintain reversibility, the reaction must occur in a closed system. This means it happens in a sealed environment where no particles can escape. At time zero in a closed system, you only have reactants. The forward reaction operates at its maximum speed, while the reverse reaction is completely dormant because there are no products to break down yet. As the reaction proceeds, the reactants are consumed and the forward reaction slows down. Simultaneously, the products accumulate, giving the reverse reaction the material it needs to accelerate. Dynamic equilibrium is the exact moment the forward and reverse reaction rates become equal. Overall concentrations stop changing. Importantly, equal rates do not mean equal amounts. A system can stay locked at equilibrium with 80% reactants and only 20%. In the late 19th century, chemist Henry Le Chatelier codified a rule for these systems. Le Chatelier's principle states that if a system at equilibrium experiences a change in conditions, it will shift its position to oppose that change. In any reversible reaction, one direction is exothermic, meaning it releases heat, and the reverse direction is endothermic, meaning it absorbs heat. If we increase the temperature of a closed system, the system attempts to cool itself down. It opposes the added heat by shifting the equilibrium position in the endothermic direction. Conversely, if we decrease the temperature, the system acts to replace the lost heat. It shifts the equilibrium position toward the exothermic direction to generate thermal energy. Temperature acts as a thermal steering wheel. Chemists use it to deliberately push an equilibrium heavily toward the side of the equation that produces their desired chemical. We can also manipulate pressure, though this variable only affects reactions that involve gases. The system's response to a change in pressure depends entirely on comparing the total number of gas moles on the reactant side versus the product side. When we increase the pressure, the system opposes the crowding by shifting equilibrium toward the side with the fewest moles of gas. If we decrease the pressure, the system shifts toward the side with more gas molecules, generating more particles to build the pressure back up. The final theoretical lever we can pull is concentration. If we add a large amount of a specific reactant to the system, its concentration spikes. The system opposes this sudden excess by speeding up the forward reaction to consume it. This shift in concentration forces the equilibrium position to the right, naturally generating more product. By combining Le Chatelier's rules of temperature, pressure, and concentration, chemists can break a system out of equilibrium and trap it in a state where it continuously forms products. The ultimate industrial application of these rules is the Haber process, which synthesizes ammonia. The chemical equation is nitrogen gas plus 3 moles of hydrogen gas, reacting reversibly to form 2 moles of ammonia gas. Thermodynamically, 4 total moles of reactant gas combine to form 2 moles of product gas. Furthermore, the forward reaction is highly exothermic. This graph shows the theoretical setup for maximum yield. According to Le Chatelier, forcing the absolute maximum amount of ammonia requires extremely high pressure to favor the side with fewer moles, and extremely low temperatures to favor the exothermic direction. But this creates a kinetic paradox. Low temperatures guarantee a massive theoretical yield, but they drain the particle's kinetic energy. The molecular collisions become incredibly rare and too weak to overcome the activation energy. Heating the vessels solves the energy problem. The particles collide aggressively and react incredibly fast. However, the high heat forces the equilibrium entirely to the left, destroying the ammonia yield. This is the central dilemma of industrial chemistry. Achieving a perfect yield that takes centuries to produce is economically worthless. A lightning-fast reaction that produces almost zero product is equally useless. To solve this, the Haber process operates at a specific canonical temperature, 450 degrees Celsius. 450 degrees Celsius is a calculated mathematical compromise. It sacrifices the maximum theoretical yield to ensure the particles retain enough kinetic energy to produce ammonia fast enough to be profitable. The system also operates at a canonical pressure of 20,000 kilopascals, or 200 atmospheres. Pushing the pressure even higher would mathematically increase the yield. However, 200 atmospheres acts as an economic safety ceiling. Beyond this point, the specialized reinforced pipes required become too expensive to build and too dangerous to operate. To maximize this compromised setup, engineers use a final chemical tool, an iron catalyst. This energy profile diagram shows the catalyst lowering the activation energy barrier. This speeds up both the forward and reverse reactions equally. The iron catalyst does not shift the position of equilibrium, and it does not create more ammonia overall. It simply forces the system to reach the 450-degree compromise much faster. This specific chemical manipulation is what allows us to synthesize the millions of tons of ammonia required for global agricultural fertilizers. The Haber process demonstrates that chemistry is about mastering the rules of equilibrium to align natural mechanics with industrial demands. Take the guesswork out of chemistry revision. Visit www.studybuddy.tech right now to execute your diagnostic test.